There you go. So, welcome everyone to our very first career spotlight. We are spotlighting what it's like to be a STEM researcher, life in STEM research. I am very excited to introduce to you Richard Thornton. Um, Richard is so generous to have donated his time tonight so that we could learn a little bit more about his career path. Richard earned his Bachelor of Science in Biological Engineering from North Carolina A&T State University in 2017. Over the next 2 years, he completed a post-bac research program at Beth Israel Medical Center in Boston through Harvard Medical School. While there, he focused on breast cancer research on cell communication, using a pathway that is critical to cell growth and proliferation. Currently, Richard is in his second year in the molecular biology PhD program at Princeton University. The goal of his research is to assess how dynamic cell signaling can affect cancer's ability to spread and resist treatment. Richard is excited to talk to students who are thinking about or want to know more about a career in scientific research or graduate level studies. He is also happy to discuss the similarities and differences between bioengineering and molecular biology. So, Richard, welcome and thank you.
Thank you for the introduction.
You're welcome. There we go. Um, so, I just wanted to first off, even though we read your introduction and your bio, if you could just tell us a little bit more about you so that we could get to know you, especially for some of the younger audience members on the call.
Yeah, sure. So, as you said, graduated from North Carolina A&T State University, majoring in biological engineering. I'm originally from Maryland, so about 2.5 hours from where I am right now, up in Princeton, New Jersey. I've always liked science. I knew that somewhere, some way, I was going to end up doing science. I never didn't really know what that was going to look like until maybe middle school or high school, but always like biology and chemistry. Outside of just science and academic things, I love photography. Kept it as a hobby. Thought about turning into a side job a couple of times, but yeah, really love photography. Shot some events, some friends' weddings, and aside from that, like sleeping. Yeah, and reading fiction and fantasy. So I think that's a good generalized overview.
That is a really good overview. So let's talk from the beginning. You said that you kind of didn't know what it looked like to be in science until middle or high school. How did you determine what you wanted to major in college? What courses did you take in high school? Did you do an internship that helped you solidify that? Talk to me about that process.
So my high school was interesting in the way that it wasn't a fully a magnet school, but it had a program that was called Science and Technology, which is basically a small bubble within the school itself. That we had two other sister schools in Prince George's County, Maryland, that did similar things. So in that bubble, in that program, we were actually basically we had many more classes in science, technology, and just STEM fields in general. So that basically kind of funneled me towards more STEM oriented careers by just the nature of being in that program. And as for internships, one really good aspect of the science technology program at my school was that they actually had you were required in your senior year to take some form of internship at one of various locations in the immediate area. They could be from NIH, University of Maryland, which is actually 15 minutes away from my school, or luckily enough, there's also a NASA Goddard Flight Center in Greenbelt, Maryland, which is just down the street as well. So there was pretty preeminently placed for a lot of STEM research in various fields. The internship that I ended up doing was at University of Maryland, and I worked in metabolic engineering, so another just fancy type of engineering. Basically, I looked at algae and how the lab that I was working with at the time was seeing the best way to maybe utilize algae as a biofuel. So that was a really, just one of my first real experiences with just hands-on research, working with graduate students and seeing kind of what university level research was like. And I think that definitely was very helpful for me.
That sounds like it was really helpful and also a really cool experience that you got to get some hands on experience in high school before you got to college. Is there anything else that you wish you had known? It sounds like you had a lot of exposure in high school, but is there anything that you wish you knew before you went to college?
Um, let's see. Academics wise, I think I did know a general enough, like enough before just going into college, because the preparation for college, there's not so much you can do, because it's just a whole new way of existing and way of living. You're just on your own for the first time. You get to actually find yourself. So I guess maybe the recommendations that I would have for like what I wish I knew before college would be maybe more on the interpersonal and social side, because when you go to college, while you're at college, it's a very unique like time in your life, and everybody like finds themselves to different degrees while you're in college. And I think going into it with a mindset of not trying to stay the same necessarily as you were in high school, you could definitely still follow your passions, your interests, but you have so much more potential for growth while you're in school. You have all the many people that have similar interests to you. You have all the resources just around you that are literally dedicated to you, basically going into the different things, finding out, oh, is this interesting? Is this what I want to do? So one thing I would maybe tell me in the past would basically be more proactive in finding some of those various resources, both on the academic side and on just the personal, even social side. Because I remember like maybe junior year of college, I felt like, okay, I feel comfortable just in the space that I'm in. And then I felt like I was able to take more advantage of just college as a whole. And for me, as a dedicated introvert, I that doesn't surprise me too much. So it took me a little bit of a time to kind of warm up to the whole college experience. Even though I had friends, things were going perfectly fine. But it just takes a while to like feel comfortable in yourself to actually do the things you actually want to do and get to the place you want to get to.
Yeah, I can definitely resonate with that. It's like nothing else, really, and after you leave, you'll never really experience anything like it again. It's this little snapshot, but I love what you said about taking advantage of some of those resources and taking time to really find yourself and figure out who you are. While you
Mhm.
were at college, I know that you were an engineer. Can you talk to me a little bit about what it was like to be an engineer and specifically a person of color, a Black male engineer on college campus?
Yeah, so I personally had a great experience being an engineer, as an engineer on a college campus. My school is North Carolina A&T State University. We are actually the largest producers of minority and Black engineers in the country, as the largest HBCU. So our engineering program is very well known, and it does prepare you for being a professional engineer or like pursuing pathways, career paths after that. So the engineers, there was a vibrant community essentially, because there were just multiple types of engineers just on that side of campus. There are many just different activities that would just be kind of in and around the engineering community. And so you would just see the same people. You worked in and around like the same couple of buildings oftentimes. And it was just a really great space. And I think it was definitely useful in like setting my perspective, which as I've gone out of college and into the wider world, I see that's not the norm. But it was, I think, very useful to have my baseline of what an engineer is, what STEM people in the STEM fields are, just be primarily like people of color, people that look like me, and just people that have maybe similar goals to me. And while like I said, I know that's not necessarily the norm, I think it's been very influential in maybe how I just feel like view my own place in just the greater maybe academic landscape, or even like wider than that. Because even though there has been maybe some feelings of maybe imposter syndrome here and there for different reasons, it was never, I feel like, for like the reason of like, oh, I can't be like an engineer or can't be a scientist or anything like that, just because I had been surrounded just by very smart people, many smart people that were just had high goals and were achieving these goals and doing amazing things throughout my entire like undergraduate career. So I definitely was very blessed to be put into that situation, and I think that's definitely like maybe something to consider, depending on like where you're thinking about going to college. Like, what is the actual landscape of these institutions actually look like, specifically just overall, and what the landscape like in your maybe research area or like major area of choice look like, because different colleges of different sizes can have different environments and ecosystems based even siloed within different majors. Because for instance, I don't fully know what maybe the humanities side or the like business school side of my campus, like what that culture was like. I know it did exist. There's many, like I know it was there. I didn't that just but that's not where I was. Yeah, just kind of thinking about the area that you might be in once you go into college would be really useful. And one thing that could help with that ecosystem, that area, would be student groups. So for me, that the primary one was NSBE, which is the National Society of Black Engineers, was very prominent on my students on my college campus. And I actually went from being a general member to actually being in the leadership at the chapter level. And then by my senior year, I actually went to the regional level, which was being a part of the organization and like trying to manage communication from Pennsylvania down to South Carolina. So that was definitely a formative experience, just that which tied completely seamlessly like into just that engineering experience, especially like just that Black engineering experience at my campus. So I'm sure student groups across college campuses are very integral in shaping this community. So definitely just keep that in mind as you look for these different things.
That's really, really good advice. I think what you said is so important about being in a community where there are people that look like you. And I think that can be true whether you're a Black student in the STEM field or a woman in the STEM field. I know that there's still a lack of gender parity with women in STEM and feeling like I'm surrounded by all men. And so I don't see myself in any of these leadership positions as well. So I think no matter kind of what affinity group, you relate to, I think it's important to be in a school that has either a student group like NSBE or a Society of Women Engineers or anything that can really help ground you into, hey, I have people, I'm not just on my own. There are other people that look like me that are trying to do what I'm trying to do. I did want to talk a little bit briefly though. We talked about how important it was for you within engineering, but you mentioned that you went to an HBCU, which is a historically Black college and university. Can you talk to me to the extent that you know, because we all only went to the one college that we went to, but you've had experiences now with an HBCU and also with, the Ivy League institutions, which are predominantly white. Can you talk to me a little bit about the difference in the culture and feel of an HBCU?
Yeah. Um, hmm. It is definitely different, and it's also the time period at which I experienced each institution is also very important. So the I guess community in the feel of HBCU is definitely, it's difficult to explain, but for me it's like maybe a sense of home, a sense of familiarity. For me it's definitely that way because my family has gone to that, like I'm third or fourth generation. It's like, so like like my father, my mom, my grandfather, my dad's side, and my great grandfather just all went to that school, and now my brother goes as well. And my grandmother lives maybe 10 minutes down the street. So like my family is in that area, in that community. So that's definitely one of the reasons it does feel like home. But even aside from that, I know that my experiences at A&T at an HBCU definitely did feel home. It did feel like comforting, because that was just, there was never the feeling of looking around and maybe not seeing people that look like you. Just the recognition of difference is enough to possibly cause maybe some feeling of comfort or even discomfort if it's not there. And like I said, the timelines for when I experienced these different institutions is very important. Your college years are some of the most formative years, and then after that, you are quote unquote an adult. It's definitely still much to learn, but my time at Harvard for my post-bac was definitely a bit different. And now my 2 years here at Princeton, like where I am officially a student, it's I can definitely tell just the difference, like being on the graduate school side versus being on the undergraduate side. So like I'm definitely part of the school, but it's to a very different degree being part of the school. So because the graduate school life is, yes, there's some classes, but a lot of it is just, self-driven work versus when you're an undergrad, you're going to all these different classes. You see like all the same, like different people, like some of the same people, but then they shift based on the classes you're taking. And it's just like volume wise and just the amount of connections and socialization is definitely a lot higher on the undergrad level. And excuse me, and at Harvard and here at Princeton, definitely am very cognizant of just the diversity comparatively that I've seen, because being at the HBCU is relatively like homogenized of black people, which was very great for me just to see everybody thriving and living. But again, that's not how the wider world actually is. So it's very interesting to see what higher education institutions, how they place diversity within their various cohorts. And one thing that I was seeing that in my molecular biology cohort, I think the math worked out to essentially was it 12.5% of like African Americans like in my specific cohort, which is I think somewhere around or exactly at like national average percent of like breakdown, which was very interesting. So that number seemed very tailored, and it's just seeing that difference compared to pretty much maybe 92%. It's just a random number, but primarily Black African Americans, like for the majority of my undergraduate career. It's definitely something that I was cognizant of. I don't necessarily feel less or like discomforted by the other institutions that I've been in, and I think a large part of that was because I felt, I guess, grounded enough in my undergraduate year. So I found myself enough that I felt confident to kind of go out into the wider world and feel that I could still retain like my sense of self or like the general purpose of like where I wanted to go. And I think, yeah, definitely choosing a college that can kind of speak to that part of you it's really difficult because you don't know what you're going to grow into before you go through the process. But I think that is definitely something that happens through the college process. And I do think that I was, I guess, prepared enough to kind of exist and definitely try to maybe thrive in these various environments after coming out of undergrad.
Thank you. I think that I think that makes a lot of sense. I think it's good for students just to keep in mind the differences. I like to expose all my students to the different um, kinds of college environments that they can find themselves in and how it shapes everything that we do, shapes us as a person. I believe that everyone ends up where they're supposed to be, but it's nice to see the interplay between those two different kinds of schools for you. Now, I want to dive into the academics, the science of it a bit. And I don't know much about science, but I would love to know, how did you decide after college that you wanted to go into biology instead of bioengineering, which is what you got your degree in?
Mm-hmm.
And I would love for you to also talk about the differences between bioengineering and biology.
Yeah. So it's the differences between the two. So the biology at the like largest, most general scale is essentially math. All engineering requires just higher level of math, generally calculus and calculus-based physics, just pretty much every type of engineering that I can think of does require that, and biology requires much less math. And just depending on the area you want to go into, there's a different level of understanding required of just areas of biology. So for the like microbiology classes that I took, like they go over just maybe the central dogma. So you got like RNA, DNA, cell, genes, like, just very base level stuff, like all, like bioengineering, you need to know these things. And I guess for some more differences, it can also depend on the actual program description at the university. Bioengineering is kind of an amorphous term. So at my school, they also had biomedical engineering, which is more focused on like medical devices. So kind of like the physical side. So where you would need to know how to construct or maybe even like maybe operate some medical devices. So you would need to know some biology to see how these devices could be maybe like maybe prosthetics could actually work with the human body or just biological interface. So you need to like you can't just build something and if it's going to cause harm or damage to a living person, that's not going to be useful. So you have to understand the biology side behind that, not just the engineering. Then there's also the biological engineering that I did, which was like they had various courses that were more like natural resource side, which would be like agricultural science, because there is engineering in that, basically structuring um, farms or just growing things in like sustainable ways, or also just the development of biofuels also takes engineering, like I mentioned before, like my high school internship. And then there's also the bioprocessing track. So that's can also be basically using chemical engineering processes. So thinking about how different chemical reactions can occur for the maybe process, the intention of making drugs, or just thinking about how energy is transferred to maybe make a system, like a machine or a system, more efficient, and then like possibly integrating that with biological materials, such as maybe like larger scale, like vaccine production or things for that nature. Like there's specific processes that have to be followed, because it's not just like you can't just churn out like a piece of metal that has some holes cut into it. If you're working with biological material, you have to be able to like to scale something up, but also make sure that this living thing or something that was a piece of a living thing, or in the case of a virus, just biological material in general, is actually stable and still usable at the end of the process, while also making sure things are efficient and actually at the highest quality that you need. So there's a large, I guess, range of what biological or bioengineering could mean. And biology just by itself is generally also just not an end career goal, because you could be a biological or biomedical engineer, like maybe at a company or at a institution. You may or may not be just a biologist at institution or just a job. That's very, very general. You're probably going to be something much like more specific. You could do just the research that you're interested in, whether it's maybe like cancer related, or like neuroscience. Like you'll delve more specifically into like realms of biology as you just pursue the straight biologist pathway. And many people who do study biology also can go into the various aspects of the medical field. So that's like the main difference. Some engineers do also cross over to the actual like practitioner of the medical field, but it's I think a lot lower percentage wise than the people who are just thinking maybe straight biology.
And the driving force for you, the decision that really came to, I don't want to continue pursuing bioengineering. I want to get my PhD in molecular biology. How did that come about?
It was in close to my senior year. Yeah, because they prepare you. My school prepared me for this exam, which is called the FE, or the Fundamentals of Engineering exam, which is the first step in becoming a licensed professional engineer, which is an actual title. You get to put it after your name, PE, after like just like PhD or anything else, which actually is a mark of you being an engineer, which is basically your say so on whatever projects go on is the law for that specific thing. And that's not really like when I was studying, or like the classes that we were taking to prepare us for that, I realized that that didn't actually excite me the way that I feel like if a career should excite you. And it wasn't gelling with myself particularly well. And I knew I had always felt a lot more enjoyment and a lot more positivity from just biology and maybe some of the chemistry that I also done. And so after my junior year, I actually did an internship, a research internship at Dana-Farber Cancer Institute up in Boston, and that was pretty great. And that was one of the more extended, just straight biology cancer adjacent things that I had done up to that point, and that was very cool. And it didn't have any engineering, and I was like, okay, this can work. And so through my senior year, when they focused even more on just like the really engineering heavy parts of things and much less on the biology side of life, I was like, okay, I definitely need to do more biology because I feel like that's where my calling is. So that's how I decided to make that switch to biological research instead of just engineering. And I still think in some ways will use and have used my engineering training. The lab where I am now has a really solid mix of people who are just biology and majors, people who are in the bioengineering program here at Princeton are in my lab. And just what we work on is um, there are aspects of like approaching a problem and problem solving that they teach you as an engineer that I don't think are taught in the same way or focused on in biology, because in biology there's rarely like one answer, like because things are system wide, or like, okay, why is this happening, and like the questions can be open ended. And because that's how it is for like a lot of science. But if you have math or engineering, things are a lot less open-ended. Like there's an equation, you solve the equation, cool, there's an answer. And I do like that. I do like some of that aspect. There are times when I think I like one side more than the other. Let's say it's like when something's just not working the fifth time you did it in just biological science. It's like, okay, I'll tweak this other thing and try again. Versus, okay, I solved a problem. This shelf or this device that I made works within expected parameters. It is, very straightforward, linear. And I think having aspects of both, so just keeping the bioengineering, so mixing the two is very useful. And I think, especially for the way that my brain works, like I do like to solve problems, and having constantly shifting problems that don't have a solid answer can get difficult at times. So I think having maybe working with some things that are a little bit more straightforward, and also like maybe working around people who have that mindset, at least part of the time, can be pretty useful for me.
Thank you. That is a really good breakdown of the differences. As you know, I'm not super science literate, but I love that you kind of talk about, the definitiveness of one field and the kind of more fluidity of another field. I know, though, that when you graduated, you decided to get a post-bac, and I'm not sure if that was purely because you were switching. So that kind of goes into the question of like, how difficult was it to switch from bioengineering to biology? And then is a post-bac a common thing? How do students get a post-bac? What about some of those internships that you talked about? How do you go
Mhm.
about getting these opportunities, and why are they important?
So I do think my primary motivation for uh, do, uh, taking a post-bac position was the fact that I was switching and that I didn't have a lot of the research experience that I would need to apply to grad school. Because one thing that is another difference between the engineering side of life and maybe the biology side of life is they focus on different things in terms of maybe internships or work experience, like through the college process. So I did focus on, like I said, for my summer internship, I did go up to Boston and work as a research scientist for like a summer. But for like in biology, that's like you are pushed to do that much earlier so that you can have a lot more hands-on research experience in the field of your choice. And like, because I started my transition later just in my college career, I feel like I did not have enough experience basically for myself to feel comfortable, and for to build up basically a strong research resume. Because when you're applying to grad school that's in the biological sciences, the research done is one of the main things, if not like the most like important thing that you can actually have. And so if I, up until that point, I had a summer a full summer between junior and senior year, and maybe like a month or two of working on some other project that was like on campus, and that was not enough for me personally. I was told by a couple of people that I could apply and probably would get in, and I feel like that was true. Like there are many different grad schools, and grad school itself is still a school. Like you can definitely still learn a lot of the, excuse me, the things that you would need to do for research, but I did not, just like I said, didn't feel comfortable enough in my own abilities and my own self. I guess like seeing myself like as a research scientist that could actually perform to actually apply to grad school at that time. So I applied to a post baccalaureate program, which is a post bac, and the way that I did it was a bit serendipitous, I suppose, because the person that was in charge of my summer research program between my junior and senior year was also in charge of the post-bac program at Harvard. So at the end of that summer program, I kind of like told her that, yeah, I'm pretty much thinking of doing grad school, but I also like told her that, yeah, I didn't think I was ready right now. She's like, yeah, so apply to this program. And so I did. I also applied to several others, because many of the post-bac programs in the biological sciences are funded through the NIH, and they're at various schools. They're called different things, but they're most under the NIH PrEP program, so PREP, Post Baccalaureate Research Experience Program. And various schools, like I said, have different names, but that's likely where they get a lot of their funding from, is like from that NIH program, and they're usually 1 to 2 years. All of them are 1 year guaranteed, and then some of them have flexibility for going an extended, one more extended year. And they are the purpose of these programs is to give you more in-depth research experience to basically strengthen you as a candidate for graduate school. The majority of them are not degree granting. I don't think any of them are, because this is a preparatory program before getting into grad school. Um, some, you probably, depending on the actual rules and regulations, some might actually allow you to take classes at the institution that you are doing the program at, because you have like a quasi grad school status, so you can participate in a lot of the graduate school organizations and functions and privileges at whatever institution that you do join. So that is actually very nice. It does give you a taste of kind of like of grad school without fully being in grad school, which is nice but also bittersweet. Especially like because if you form connections, or you start feeling a sense of belonging, but you're also like not technically a full grad student at that place yet. So it's like it is very useful, especially in determining if this is the path that you want, because it does give you that taste of grad school. So if you are maybe questioning your desire to do graduate school for a PhD, or even like maybe a master's in whatever given field, a postbac I think would be very beneficial, because most of the ones in biological sciences are essentially kind of a job. So you don't pay them, they pay you to do the research. So, and it's not, granted, it's not too much. But again, grad student stipends are not known for being exuberant, but it is enough to get by. It's enough to enjoy life and sustain. I've done it. And I think it's whether you want to use it to like build up momentum to definitely go into grad school, or use it as the deciding factor to decide yes or no on grad school. I think both are very valid, and it's very useful for both. So like if you're looking them up, the NIH I think has a list of them on its website. And if you maybe are interested in a school, or and then maybe a specific school, you can also just look that up as well. And if you just type in like the school's name, and some combination of post-bac or prep, or anything kind of like that, you should probably be able to find the resources relating to that.
That was very helpful, and kind of a nice, clear chart on how you can get into that path. So I want to delve into your PhD a little bit.
Mm-hmm.
Can you tell me maybe what's your favorite thing and your least favorite thing about getting your PhD, and something that you never would have known about being a PhD doctoral student?
Mm-hmm. So favorite and least favorite is the same thing, which is weird. It's like the flexibility. So you are in charge of doing things. So it's the difference from undergrad and grad school, where in undergrad, you have all these classes, the teacher assigns the thing, they might send you a nasty email, like if you don't turn in your essay or do your things. But in grad school, like you applied, you worked hard to get to this extra level of school. You've at least completed some level of undergrad by all, like, in the eyes of the law and everybody else, you are an adult. So like they you have to have the desire and kind of like the motivation to do the things. So that's really good, because you choose what you want to like research, what you want to look into. You have like freedom in a large sense to kind of do what you want to do, in terms of academics and even free time and whatever. Like in college, you definitely have a measure of freedom, especially like before, compared to the life before that. But then in grad school, that's increased more so because there are many fewer classes. There will still be some classes just for the degree requirements, but for Princeton specifically, there are only 4 required classes, which are taken like just in that first year. And then you take like a general examination after you get placed into a lab. And then you don't have like another class until maybe second, third year. It's like one ethics course. And then that's about it. So like there's only like 5 mandatory classes, which is very different, because 5 mandatory classes over the course of maybe 5.5 years is very different than a college, like, a 12 to maybe 15 or 16 hours of coursework, and undergrad schedule. It's just very different. So just like the level of freedom is really great, but it's also kind of, it can be not great at times, especially if you maybe are not as motivated sometimes, or you like have difficulty like maybe staying on task or like having that self-motivation. That's where like advisors or like having like a support system in place comes in, like actually who can maybe nudge you along or pull you forward, however you need that to be. But like that's one of the biggest, I guess, changes that can be great but also not so great at the same time. Yeah, it's really kind of wild.
So speaking of that flexibility, could you walk us through like what does, if such a thing exists, your typical day look like?
um, so let's say a typical day. I wake up. So yeah, speaking to the flexibility, I am not a morning person. So I'll try to I wake up maybe something like 8:30 or 9 or something, and then maybe try to get to lab by between 10 and 11, something like that. Various, depending on like what I have to do. Stay in lab. I might go out, like get something for lunch, or might just like eat an early dinner when I leave, and then I usually like stay until like maybe 5:30 or 6. It could be earlier some days, it could be later. It's really depends on what experiment that I have running. Some might take a couple of hours to get set up, and then maybe I'll come back like later that night to check on it, or maybe I'll set something up at the end of the day to run overnight. Like it's really depends on like what you're doing like that week or like at that day. But the flexibility is, again, like you are a full grown person. You are the people that are working beside you, like all your fellow grad students or postdocs, people who already have their PhD that are working on their projects, and then your PI, the boss of the lab, the principal investigator. And a lot of that, the lab culture, like how the PI runs the lab, can depend on essentially like what your schedule looks like and how that flexibility actually works out. Some PIs expect their lab to be in like 9 o'clock sharp and don't dare leave before 5, so they treat it like a job. Others, which are like mine, are very flexible. It's like just do what you need to do because you're doing this because you like to do it. Like I'm not going to force you to do the work. You are here because you want to figure something out. You want to do the science. So I'm going to check in on you. I'm going to help you as I can. I'm going to give you advice, help you troubleshoot things. But it's like I'm not going to like maybe super be a taskmaster and to make sure that you're dotting all your I's, crossing all your T's. So I could come in at like noon or one day, and then maybe stay a little bit later, or just maybe come in for like a couple hours one day, and then because I just didn't have much to do or just didn't really feel like it, or just maybe not go into lab, maybe just shoot my boss like a text or something on Slack, hey, I'm not feeling it well, or it's like, oh, just not coming in today, blah blah blah, and then cool, then I'll come in tomorrow, do what I need to do. So like there is true flexibility in that sense, but it definitely depends on you, like as an individual scientist, how you are getting your work done, and how your PI, the head of the lab, is what your relationship is there. But there, I do really enjoy that because it doesn't feel like I have to do anything like, oh, I'm going to get scolded, or like, a mean email or anything like that if I don't like go in exactly at this time. So it is kind of a freeing thing. And that's probably a very unique thing to grad schools, because I know many occupations are not as flexible and understanding that you can kind of do whatever you want whenever you want.
No, I didn't experience that until I was my own boss, and even then, sometimes I don't experience that. What are weekends like? Do you get vacations? Do you get breaks?
Mhm. Um, so weekends, it also varies depending on like what's going on. So it's like maybe in some more crunch times, like some of the weekends are essentially just like another day that I would wake up and go to lab at approximately maybe similar times, probably probably a bit later. But uh, a lot of people just don't come into work on the weekends. I think I generally I'll maybe go in for an hour or two on one of the days of the weekend, and then that's about it. So Saturday or Sunday, and then just kind of chillax, do whatever I want for the rest of the weekend, or maybe going around, maybe taking some pictures, or just chilling, watching videos at home. The pandemic makes things a little bit interesting, so maybe a little bit more of the home thing as of late, but hopefully that'll change as the summer rolls around. And so yeah, you're not super beholden. Like you do definitely do get some vacations. The nature of biological science is a bit the wet lab science, so actually like working with cells, so like having things growing and then like doing analysis like on cells makes things a bit interesting for like longer vacations. So I could maybe, if I wanted to take like a day or two off, I could set things up and so that I wouldn't have to really change anything and just kind of do that. But maybe anything longer than a couple of days, I would actually very likely have to kind of shut things down in a way, because like I said, the cells are growing and you're doing specific things with them. But if you can't just leave them growing and then they die and they get unhappy and unhealthy. So you essentially would have to I would have to like collect them all the cells, freeze them down, make sure like they're all happy and like that, and basically kind of and take however long of a break, like maybe a week or two, and then like after that come back in and like thaw everything, start growing them back up, and basically get the ball rolling again on, so I could do some more experiments and like research and things. So it is a little bit definitely different because you can't just up and leave. uh, there's usually something kind of constantly going on like in the background. But as for the overall vacation, I think technically we have 2 or 3 weeks of vacation. I think that's in like the graduate school handbook or some official thing. I don't really know how people, I don't think PIs or the bosses usually adhere to that super strictly. Again, it's depends on like the relationship you have with the head of your lab. Obviously you're not going to just be taking like every other week off. You have to get something done, but I think most people are able to take excuse me, like just summer vacations whenever they feel like it, or and like a winter vacation whenever, like without really any issue. So yeah, vacations definitely work out. Yeah, so it's definitely pretty flexible there too.
Awesome. We have just a couple more questions, and then we're going to get to all of the questions that I know my students have. So definitely, if you're listening, make sure that you are getting your questions together to either put them in the chat, or you can ask your questions live too if you want. But I just wanted to give you guys a heads up that we're almost at the Q&A portion. I would love for you to actually just talk to us a little bit, not as in depth as I know that you probably could be, but just a little bit about your research, so that they can kind of understand what you're doing.
Mhm. Okay. Yeah. So my research, as Sydney covered, like in the very beginning, is looking at cancer and cell signaling. So that in cancer and in just all types of cells, there are these just way that cells communicate with each other, and we just generally call that cell signaling, just as a broad term. And what that generally is are just like little molecules that come from like outside of the cell, that can sometimes be like either circulating around the body, or maybe that one cell basically secretes out to talk to another cell other places. And basically the way that these signals are internalized and basically interpreted is it's called like signal transduction, because what it basically is a kind of like a game of telephone. Once one of these molecules basically reaches a cell, they bind to a little receptor like on the outside of the cell. Then that triggers like multiple steps downstream, like basically like dominoes falling down. And then eventually there's like a response happens in the cell, whether that's a signal for the cell to like grow or divide or move or do anything really. That's just like a really broad overview of like signal transduction. And what my lab in particular looks at is one of these molecules. It's called ERK, which stands for extracellular regulated kinase. So just for signals that come outside the cell, extracellular. And the kinase is the name of a protein that actually phosphorylates, or just like turns on something else in the cell. And what this pathway, this specific protein does, it is implicated in a lot of different things, but a lot of it is definitely is cell growth and the division, which is very important for just cell health normally, but also in cancer, because in cancer cells are growing too much or they're dividing too much, and that's not good. The body can't compensate for it. So what we're looking at really specifically is like how those signals are actually interpreted. So it's not just like an on and off. So it's not that you just have like something on binding to the cell and then you just get like a plus or like on signal. And then once it's done, it goes off. That's not actually how it happens. There's actually what we call like pulses or dynamic signaling. So it'll be on and then off and then on and off, or maybe like on really, really high and then off, and then it waits for like a couple hours, and then it's on really high again and it goes back off. So just there's these different types of frequencies for this signaling or the cellular communication. And these different types of cellular communication actually result in different things in the cell. So you can use the same pathway, but if you have basically an on signal, you might get the cell to basically transform into a different cell, like differentiation. Or, but if you get a pulse of activity, so just on and then off, then that could be just cell dividing. So you could actually control, or the way that the information is actually being interpreted or like entering into the cell actually can control or impact what happens in the cell. And this, we think that this is important in cancer, because it's a couple of papers and some research is like kind of showing that cancer cells are generally always on, which can make some sense. Like, okay, like you're doing a lot of growth, division, like there's no stopping anything. But it seems that some cancer cells might be able to have some of these pulses, which might let them actually basically resist different treatments, because the treatments are really designed to target the cells that are always on. But if some of the cells are able to like do always on and also do like a pulse, then the pulsing cells can actually still grow and survive even when some of those other cells might not be able to do that. So that's like one area that we're looking at. But also it's just we're not a lot is actually known about these dynamics. So the overview that I gave was what we have seen in some context, but maybe like in like skin cells or in both humans and in mice. But we haven't been able to look at a lot of these dynamics in various places because it's actually really hard. How do you see a cell basically having different amounts of activity? You have to generally stare at a microscope, and usually like the cell will have this fluorescent reporter, so it's a protein that glows pretty much. And whenever this activity happens, you see the glowing protein. Pretty straightforward. But it's really difficult if you're trying to look at a lot of cells. You can't just look at an entire like mouse, for instance. Like you can't just have a microscope and just look at every single cell in a mouse. That's impossible. It's not going to work. So what my lab is actually working on is actually we have a system that once a pulse of that activity happens in a cell, it produces a green fluorescent protein or GFP, and it stays there. So it doesn't just just form the protein and then go away. So anytime that pulse happens, the protein is produced and it just kind of stays there as a marker. And that basically allows us to look at that cell and say, okay, that cell had a pulse. And now we can actually like look at that cells or those cells that actually had a pulse of activity and actually investigate what is really like going on with those cells. Because like I said, we don't really know what the pulses are doing because we haven't been able to like pick out the ones that are pulsing and actually study them further. So that's what me and the rest and some people in my lab are actually working on right now, and seeing how investigating those cells, especially like in the context of cancer, how and why those cells are different, and if that can actually be used to maybe form like maybe more accurate treatments or just like expand the overall understanding of like how cancer works, because it's still very much a mystery for a lot of the aspects of how cancer works.
And where do you plan to go with that research? Like with a PhD, what are the different career opportunities that you have? Would you continue what you're doing now? Would you do something different?
Yeah, so I'm currently thinking more of biotech or like maybe biopharmaceuticals, basically the quote unquote industry path. For a while, the career paths out of a PhD were relatively like there's like two paths. There was academics or industry. Academics being like you want to be a professor somewhere, you want to teach, you want to be like teaching somewhere essentially. And then the other part being industry, like you're going to get a job as a scientist at some company somewhere, maybe a pharmaceutical company or just another company that's working on trying to solve some issue somewhere. Like, excuse me, a lot of smaller companies have started popping up for like anti-aging things, and for things relating to like neurons and memory and things of that nature. So that landscape has always been kind of popular because there's always going to be something like kind of wrong with the human body that people are going to try and fix. And people with money and ideas make these companies, and then they get other smart people together and let's say, okay, let's put our heads together and try and fix this thing. So that's where you get like startups, because you always hear like biotech startups. Sounds like this mystical thing, but it's basically just small groups of people with money and or ambition, or just like different amounts of those things, trying to figure out how to solve maybe one specific problem usually. And what they do then is like maybe they get bought up by a larger company. Cool, we've made a lot of money. So that's one way to maybe do it. Another way, in recent times, there's been like kind of a branching out into like science policy. As we've seen just with the world today, it is very important to have people that understand science in charge of making laws, or at least influencing laws. And that's been something that's been more and more marketed and kind of told to people that are in the graduate programs now, because um, science can do a lot, but it is going to be limited by the framework that it is in. So if laws aren't like in place to either properly keep up with science, then you have the potential for like a lot of issues, possibly like ethical issues, like maybe regarding CRISPR and gene editing, because the technology is actually advancing very fast there, and the laws just don't exist because, again, this technology didn't fully exist in the same capacity just a couple of years ago. So of course there's no laws on it. So like there's science policy is important there, but also it's important for regulating and kind of explaining like the science, like what we already have, and basically maybe effectively communicating to the public and to just like writing into law how science can be used, that we already have. And there's also just broader science communication. So just effectively telling just other scientists and just the general public of what is happening in science in a specific field, or like how these advances are actually going to be utilized, because science can be great and all, but if it doesn't actually, I guess, get to people, or if it's not known, it can actually not have as great of an effect as it should. So if you make a groundbreaking discovery, but then nobody knows about it, and you don't like articulate it well, you definitely still found out this thing, but it might just sit there. Like it might not change the world in the way that you know it can. And even if that discovery could get out, you want to be able to effectively explain like what your purpose was behind it, how it should be used, and the effectively communicating the science both in the how and the why, but also like the intent is very important, because that's one thing about like once something is discovered or maybe created, it's very difficult to kind of you can't undiscover, you can't like unknow these things. So being cognizant and just like being really aware of how to communicate and how to think about these things are they actually creating and increasing different career paths outside of the normal industry and academia sides of science. So there's various avenues that can be out pursued outside of after a PhD.
Thank you. This is the last question before we take questions from my students. I just want to know, do you have any advice for students that are interested in pursuing the STEM fields, whether that's biology, engineering, or what have you?
Mm. Let's see. I guess, follow what interests you, what always makes you like ask questions, because the STEM field as a whole, like there's generally a question you're like seeking to answer, and there's probably some area that interests you more than others, or like if a topic came up maybe in technology or like robotics or something, like how does that actually happen, how do those like robot arms at car factories like actually work, like can you make a smaller one, like if it's something that maybe like sticks in your head, definitely like follow like those types of intuitions and those things, because that's what's going to actually keep your interest enough to kind of like motivate you through whatever academic and maybe career path afterwards, like because it has to be internal, definitely at the grad school level, but even at the undergrad and like high school level, like that drive is going to be very important. And even if you don't maybe know exactly what it is, you could probably kind of point to something that interests you maybe a little bit more than something else, and maybe that can overlap with something that's easy, because those things might not be the same thing, but oftentimes it's good to keep in mind what's interesting and what is easy, and see if you can maybe combine them, because if it's something is interesting, you'll be more inclined to follow it. But if it's really hard, you might get frustrated. But if something's easy but not interesting, you can do it maybe without even thinking about it too hard. But it's probably not going to keep your interest for as long, because you can do it. You're not even really thinking about it. So maybe trying to find something that's like overlaps those two things would be really useful. And even if they're kind of like really separate, like maybe you can write really good essays just really easily. You don't even have to think about it, but you're interested in like, I don't know, like coding or like coding or something. You can probably merge those interests in like reading maybe some papers, like research papers like relate to coding or like AI, and then maybe that could actually benefit you, because maybe your typing skill or something for those essays could actually come across in coding. Maybe you're able to actually code faster because you can type really well. Like there's very well could be some interesting overlap like that. So basically think about yourself and what things would work best for you. And I think if you try and use that as a little bit of a navigation tool, I think that could definitely make things a bit easier as you pursue things in college and beyond.
That was really, really good advice. I love the advice about finding the intersection of what you're passionate about, but also not just what's the easiest, right? This healthy balance between easy enough where you will internally not get frustrated, but not too easy where you'll get bored. I want to take this opportunity to open it up to my students, and I know I have a few students that are going to be watching the recording. But I just want to know what are your questions? You can chat them, or you can uh, turn your mic off, either or raise your hand.
I have a
Um,
question.
okay, we'll
Um,
go Amanda and then Yanni.
okay. So I'm wondering where ERK is located, like within your transduction pathway, like whether it's in the beginning, because I know it's a kinase, like whether it's turned on by the ligand, like attaching to the receptor, or if it's like
Mm.
further down the pathway in like the transduction phase,
Mm.
where it is.
Excellent question. You said many good science words. I am happy. So yes, it is in the signal transduction pathway. It is basically the final step. So the very first one is really often a receptor called EGFR, which is like one of the largest or like most frequently used like receptors, and it's part of ERK is like the last step in what's called the MAP kinase pathway, or sometimes the RAS ERK pathway. And ERK is, like I said, the final kinase, and it usually is the thing that actually is able to activate various transcription factors. So that's the thing that would actually go and interact with the things on the DNA, or like the DNA itself, to actually start transcription and ultimately production of a various gene and then a protein or something. So it's like at the very end of things.
Okay, that's cool. And also I'm wondering if there are any like secondary messengers that are involved, because I know you said it goes like all the way up, like maybe they were used to like amplify the response.
Yeah, also good question. So there are positive and negative feedback loops in the RAS-ERK pathway, depending on how that pathway was activated in like the context. So like for just general cell development and just like cell growth, it doesn't need to be on, like I was saying, because when the pathway is constituent like or constantly active, that's how you get cancer. So for just like some normal cell growth, there'll be the ERK pathway will be on, and then at a certain point, ERK, I believe, actually activates its own repressor. So if ERK is a kinase, it activates a phosphatase called DUSP, and that actually removes the phosphorylation from RAS, MEC, I believe RAF or MEC, or just one of the upstream kinases that actually then reduces the overall activity of the pathway itself. There are various loops that feedback. Some will have like probably a positive feedback loop, which is likely a disease state. But in general, there is a negative feedback loop to control it in general.
Thank you.
Mm-hmm.
Great questions, Amanda. Yanni?
Right. First of all, thank you so much for taking the time out of your day to talk to us. And I was just curious. So I know you mentioned earlier that you started to find out what direction you were taking or what you were going to head towards in around high school or middle school. And so I was wondering, do you have any advice for those who are curious about STEM-based internships, but may not have like such an advanced level of that subject? Like, where would you start?
Yeah. So my advice would be to actually you ask your teachers, utilize them. I only had a couple of, I guess, advanced science classes in high school, even though like it was a STEM science technology program. I actually only took 3 AP classes that I thought would be necessary into going into like biological engineering. I took AP Chem, AP Physics, and AP Bio. It turns out I also took the wrong AP Physics because it wasn't calculus based, so I had to take another physics class in college. But anyway, I was not interested in taking the other like non-STEM APs. But the teachers of my AP like STEM science classes were very useful. I didn't, because like I said, I didn't have to actually ask them for like internships because like the program was already kind of basically I had to take an internship anyway. But I can guarantee the majority of teachers, especially like AP or honors class teachers, would be delighted if any of their students asked them, hey, what science thing can I do outside of this class? I'm sure that would just make them cry tears of joy. Because even if they aren't like necessarily in charge of a program, it's very likely that they know people or is like have an idea of the resources that you can investigate to actually see or like get into like what in like the local area like is a science related internship or something like that. So that's definitely one way to do it. As for other internships, there's probably a lot more now than when I was in high school. And a good way to do it is just look at your like the nearest university to your high school. All universities have science, many different types of sciences, and there's very likely something like a relation to the high school or like an opportunity for a high school, even if it's just like to shadow or maybe a longer term summer, or just if you end up like just perusing like the site of the universities, like, okay, I'm looking for something in biology and I'm interested in like neuroscience or something. Like if you just like go on the university's neuroscience page and you just like scroll through what the like lab members or like the people who have labs like are talking about, if anything seems remotely interesting, like shoot them an email. Like that's really random, but even though they get a lot of emails, I can guarantee that it's similar to like how your high school teacher would be excited if a PI or somebody got an email from like aspiring like high school student or something like, hey, I was interested in XYZ. Could I maybe do something? Like the people who are teachers like to help and like, you know, increase science and just knowledge in like young minds. So any proactivity on your part will probably, I can almost guarantee, be met with equal positivity. So yeah, that would be just my general advice of how to maybe find some of these opportunities.
Perfect. Thank you so much.
Mm-hmm.
Awesome. Yeah, that is a really good one. I know internships can be tricky. Matthew, did you have a question?
Yeah, I'm lagging a little bit, so but I'll go ahead. So I was kind of wondering about the whole your PhD process. Like I know with normal with school we're used to, and with undergraduate, it's kind of like you take tests and you do assignments and teachers grade that. But I'm maybe just about research based, so I was wondering how that works and how you go passing and getting your doctorate.
Okay, I think I heard enough of your question to answer. So it is, the class structure is different in grad school, but this is also very program dependent. That is another change because from undergrad to grad school, because for pretty much all undergrad institutions, you're going to have like, you know, your core requirements, like you need like a math, science, and English or whatever, and then like the things relating to your major, you have like things that you have to take. For PhD programs, yes, the number of classes is much lower, and a lot of them are going to be much more discussion based and maybe like project. Yeah, I guess maybe project based, at least in my experience. Like I said, things are very program dependent. There will be some programs or some classes that are like problem set heavy. So you actually have to do like a problem set, like maybe read a textbook, there's questions at the end of the chapter, do the things. I know there are classes that have that, but for the classes here at Princeton, there are, like I said, the 4 of them are generally not that way. They are mostly, like I said, discussion based. So you're reading papers or you're getting you have lecture slides based on a topic that maybe like developmental biology with like some related papers that might not be like super required reading, but they give you the necessary background on whatever topic it is you're talking about that week. And then you'll actually have like an hour and a half class like discussing the thing. So like you'll go over the paper, the teachers, the professors will ask like the purpose of the paper, like why some experiments were done, things that could be done to improve, or like how you would do it, or it's like it is like very discussion based, at least here at Princeton. And then for the like tests and like larger grades, there are midterms and finals. So like there's at least probably, yeah, 2 big tests for each class. And for most of them, they are big just written tests. One of them, several of the tests here at Princeton were actually like oral exams. Just because I guess the breadth of information, and they want to see like how well you do actually explaining the science. So that was interesting for me, because you basically just like you go to your different professors' rooms, because some our classes had multiple professors like over the course of the year. So we would just like go to their office, and like we had a time slot, like, okay, there's like 10 or 15 minutes. They're going to ask some random question about like protein structure, draw this amino acid, or like they ask something specific about the cell, or like one protein type we learned in class, like just things like that. But like that's like at the end of all of it, like when you've technically gone over everything, and then they're like asking you to like regurgitate it kind of like on the spot. So that's definitely a bit different from undergrad. And also the class size is very different. So the entire size of my cohort, so like my year essentially, is 27, which is, yeah, tiny compared to if you're thinking about it in terms like an undergrad class. So like, freshman, sophomore class of like, several thousand or whatever. So like the grouping of people that are going through this, you're going to see them at all times. And also like that means more attention can be put or given to like each individual student. So like if you maybe need assistance or something, you can usually get that, because again, like you're going to see the people that were your professors, you're probably just going to see them randomly all the time, because like you work maybe in the same building or like down the hall from them or something. So it's the flow is definitely different than an undergrad, and definitely from high school.
And then I think the tail end of his question was just like, what is it that you need to do to get the PhD? Like, so I know that you have
Oh,
your
okay.
general exams and you
Mhm.
defend your thesis. Like, what does that look like?
Okay, cool. Thank you. I did not hear that part. So there are, regardless, this is one thing that is constant across all PhD programs, is that there are basically 2 big tests. The general exam or qualifying exam, which happens between like usually second or third year. And that's after so you're in a lab, you're doing some work, and then you work together with your advisor to craft an idea of what you will do for the rest of your time there. And then you get tested on it. So basically, a panel of people, usually it's about 3 people, with varying levels of experience in your specific area and just in general science or biology or what have you, ask you questions, and basically you present the ideas to them. In addition to the presentation, there's a written actual thesis proposal, which is 10 pages, I think, which includes just overall reasons why you're pursuing this, like, overall importance, maybe some figures, and a rough estimate of like how experiments would be done and why over the course of, again, like the next school at this point, this is second or third year, so 2.5 or 3 years. And the committee's job is to basically test you on your knowledge of things and to see if this project is feasible, because they don't want you doing something, they don't want you proposing something that's going to take 10 years and you only have 3. That's not going to work. And they don't want you proposing something that's already been done, because it's already been done. And they don't want you proposing something that doesn't make sense. So like they are the first, I guess, stopgap or checkpoint in your whole process. And then after that, you are a quote unquote free scientist to do whatever you want. You actually don't have to, funny enough, do the thing you spend all that time and effort proposing to do. You just have to be able to think about something good enough that makes sense for like 3 years of work. So many people actually end up changing their project based compared to what they presented in their generals, because either it wasn't actually as feasible, something went horribly wrong, it wasn't actually as interesting, or maybe their advisor like changed or something, like any number of reasons, and then they end up working on something else. And then you still would have to probably you, after that point, you have a committee of people to kind of guide you and check in on you to see how your progress is going. So that's your direct advisor, who's like you just work with. And then there's just several other people with, again, experience, tangential or direct, like that would know about what you're doing, so they can check in and make sure you're kind of on the right path. I don't know how that would fully work, I guess, if you fully change everything, but I know it has been done. Many people have told me that that has been done. So I guess that goes back to the kind of freedom effort, the freedom thing. Like you can do whatever you want as long as, like, you know, you're getting some level of work done. And the final test would be the thesis defense, which is at the end of your 5th or 6th year. And some place that also depends, the severity of that kind of also depends on the school and program. I believe here at Princeton, it's more of a formality in a way. It's basically just you giving a wrap-up presentation of all the hard work you've done over your PhD, thanking people, et cetera, and telling people where you're going to be going next. I think that's what it's been. I know at other places it is actually, like, you know, a grueling test, because like technically once you finish that and once you pass that, you have obtained a PhD. So I think definitely some places make that, like, you know, the hardest test, like, okay, remember everything you've ever thought for the last 5.5 years. So like it it can definitely be on a spectrum of intensity, but it, in a way, it kind of makes sense. I guess it depends on the program's nature and environment. But again, after that, you are, I think you wait like some places tell you immediately. Like they may tell you to step outside the room, or maybe they'll turn around and let you sit there awkwardly, and then they just tell you, "Oh, you passed." I've heard multiple things from people here at Princeton and people at other schools, that also, it really differs. Some people like won't know for like a week and a half, which probably has to be a very tough week, because I don't know actually what happens if you don't pass your thesis defense. I guess you redo it in a somewhat soon time period, but because essentially at that point you probably have lined up another job and what your life is going to look like after. But yes, the majority of people that I have heard of in this program and most other programs do pass. So it's not an entirely a formality, but at that point, this is something that you have worked on for at least, like, you know, 4.5, 5 years. It's like a lot. You put a lot of time, effort. You might have published some paper on it. Like you are probably like the world's foremost expert in whatever it is you are presenting. So that level of like ownership is like, should be able to kind of come through in what you're presenting. So I'm pretty sure that's why the majority of people do pass, because yes, as long as they, I guess, show that they have done enough work that they do own that whatever science that they have been working on.
Thank you. That was a very thorough answer.
You're welcome.
Are there other questions?
Maybe can you describe like a story of a time where you were really excited with something you found in the lab? Or if you don't have a story of that, like a story where something went wrong and you had to work through it?
I guess I could do both. Let me see. So for my lab, we do a lot of like microscopy and imaging. We have a microscope in our lab. It's this like big behemoth of a thing. It's very intimidating. I was scared of it probably until like the end of last year, maybe the beginning of this year. But like as I work on it more, like I actually figure out what the heck I'm doing, like it's a bit better. And I really like imaging. It's very cool, just like, you know, just to look at cells and just see like what's actually happening, and like take these overnight time-lapse videos of like maybe 12 or 16 hours, and then you play it back, and then like they're different fluorescent proteins in the cell, so you can see different segments of the cell, like this, like maybe one part's the nucleus, and then I'm looking at how something goes out of the nucleus or back in based on whatever treatment that I did. And it's just like this beautiful high resolution thing that I was able to like completely set up with this whole crazy microscope. And like whenever I've gotten some decent data from that, just like maybe like the first couple of times I set up some of those experiments like by myself was probably one of the higher points of like where like just feeling really good about some data. It's like, oh, okay, this is what we expected to see. The cells are either like turning off, they're turning on, they look different, the drug's actually killing them, just like anything like that. And like actually being able to like fully set up the experiment and like having even some level like maybe initial analysis from the microscope video or microscope image has been pretty nice. It's like having maybe like increased level of like self-sufficiency and not just like having to be like shadowed like on the microscope because you don't know really what you're doing and you have to like have somebody do all the things for you. But then like once you do the thing yourself, like yes, I have scienced. I did a thing. That that's just generally a good feeling. And as for something that didn't work, that was like today and this past weekend or last Friday. So I spent 4.5 hours. Yeah, like 4.5 hours on this microscope looking for something, and I wasn't really seeing it, and I kind of got frustrated, so that sucked. And then today, my PI basically we kind of redid the thing I did on Friday, and he did the thing, and he basically built this microscope. So like, he of course did everything correctly, and then we figured out, oh, we were looking at the right thing, we just didn't have the right cells. So I was basically looking for something that wasn't really there. But my imaging was really nice. It was pretty, but it just the thing I was looking for wasn't there. So that was not ideal, but it means I'm not crazy. It also means he's not crazy. And it means I still did everything correctly. We just didn't, again, have the right cells. So science, that happens sometimes, but yeah, it's just like 4 hours on a Friday. I wasn't doing anything anyway.
The life of a scientist. Are there any other questions, guys? Going once. Going twice.
Maybe do you have like a book recommendation or like something related to your fields?
Molecular biology of the cell. There's like 7, 9, I don't know how many. It's like a version. It's an actual textbook. It gets like updated versions every couple of years. They use it in like upper level undergrad and some entry level grad courses. It's just called Molecular Biology of the Cell. Very useful. I had a copy during my postdoc. Actually, wait, do I have it? All right, cool. I just happened to have it. I just forgot that I had it. But yes, I have it right here. So this is the 6th edition, which is from, I got this in 2017, I think. Yeah, so they're probably on like 7th or higher. So no, you can't wait. No, okay, let me turn off the virtual background.
No, we could see it for a little bit.
I can see it? Okay.
Yeah, and I put the name in the chat, Molecular Biology
okay,
of
cool.
the Cell.
Awesome. But it's a thick text, like it is if you have AP Bio, it is the size of one of those textbooks because essentially it's like the thing that comes like after AP Bio level textbook. But it's very useful, like very, very useful. And
who is the author on that?
There are multiple authors. The first one is Alberts. What is his first name? Okay, so the authors are Alberts, Johnson, Lewis, Morgan, Raff, Roberts, Walt. If you just type in Molecular Biology of the Cell, Alberts, you'll get this book. there's like 7 authors on it.
Awesome, thank you. We've put that in the chat. And when I send out the recording, I will also link that as well. I know that some students were asking if it's possible for them to contact you afterwards if they had any follow-up questions.
Yeah, sure.
Great. I will make sure. Yeah, you can do that. You can put the info in the chat. And I'll make sure that for those that are watching the recording, they also have your email. It's just about 8:30. I can take one last question if there is one. Otherwise, we will wrap it up. Okay, well, if you guys could just thank me or join me in thanking Richard. Join me in thanking Richard for spending so much time with us today to answer our questions, to talk about his career path, to give advice for others that are thinking about going his career path. I would really appreciate it.
Thank you so much.
Thank you so much.
I really enjoyed
Thank
this.
you.
You guys are very welcome. Glad I could help out.
Awesome, guys. And like I said, we're going to be having these speaker series probably about once a month, if not every other month, but probably about once a month. So if there's a career path that you're interested in, also let me know so that we can schedule it. And, I'm just really glad that you guys could join and get your questions answered. And the recording will be on the Beyond Barriers platform. Awesome. Thanks, guys. Have a great night.
Thank
Thank
you.
you.